recording started.
Yes. Yeah. Yes, Purti.
Yes, sir. A very
Yeah,
good
please.
evening to one and all present here. IEEE Mysore subsection with IEEE Bangalore section, IEEE Information Theory Society Bangalore chapter, and IEEE Circuits and Systems Society Bangalore chapter is organizing its third webinar on solving global grand challenges with high-performance data analytics. I, Spurti B, from the Department of Electronics and Communication Engineering, on behalf of GSSS Institute of Engineering and Technology for Women, Mysuru, take this opportunity to tell a few words about IEEE Mysore subsection. IEEE Mysore subsection was established in the year 2020 is one among the three subsections of IEEE Bangalore section. The objective of IEEE Mysore subsection is to conduct various student and professional activities like invited talks, student internship, workshops, and flagship conferences. IEEE student branches of Mysore, Mandya, Hassan, Chamarajnagar, and Kodagu districts come under IEEE Mysore subsection. Currently, the subsection has more than 1,000 IEEE members and around 15 IEEE student branches. The subsection aims at enhancing professional networking and promoting humanitarian activities. IEEE Mysore subsection was inaugurated by Ms. Susan K. Land, IEEE President, USA 2021 on 21st December 2020 and delivered the inaugural address. It's honor for me to welcome our today's speaker, Dr. David A. Bader, Distinguished Professor, Director, Institute for Data Science, New Jersey Institute of Technology, to enlighten us with his knowledge. A hearty welcome to you, sir. I also like to welcome Dr. Deepa Shanai, Chair, IEEE Bangalore Section, and Professor, UVCE Bangalore. A hearty welcome to you, ma'am. I would like to extend my hearty welcome to Dr. Parameshachari BD, Professor and Head of the Department of Telecommunication Engineering, Chair IEEE Mysore Subsection, and Chair IEEE ITS Bangalore Chapter. Welcome you, sir.
Yeah, thank
I
you.
would like to welcome Dr. Jalja S., Chair IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Welcome you, ma'am. I also welcome all the office bearers and the execum members of IEEE Mysore subsection, IEEE Bangalore section, IEEE Information Theory Society Bangalore chapter, IEEE Circuits and Systems Society Bangalore chapter. I also welcome all the participants of today's webinar. I also like to welcome all the IEEE staffs and student coordinators for their support. I welcome all my fellow students and friends. Once again, welcome each one of you present here. Now, I request Sri Harshita P. to take over the session and introduce our today's speaker, David A. Bader.
A very good evening to one and all present here. I, Srihashita P. from the Department of Electronics and Communication Engineering, on behalf of GSSS Institute of Engineering and Technology for Women, Mysore, take this opportunity to introduce our today's speaker, Dr. David A. Bader. David A. Bader is a distinguished professor and founder of the Department of Data Science and inaugural director of the Institute for Data Science at New Jersey Institute of Technology. Prior to this, he served as founding professor and chair of the School of Computational Science and Engineering, College of Computing at Georgia Institute of Technology. Dr. Bader is a fellow of the IEEE, ACM, AAAS, and SIAM, a recipient of the IEEE Sydney Fernbach Award, and advises the White House, most recently on the National Strategic Computing Initiative and Future Advancing Computing Ecosystem. Bader is a leading expert in solving global grand challenges in science, engineering, computing, and data science. His interests are at the intersection of high performance computing and real world applications, including cybersecurity, massive scale analytics, and computational genomics. And he has co authored over 300 scholarly papers and has Best Paper Award from ISC. IEEE, HPEC, and IEEE ACM. Dr. Bader has served as a lead scientist in several DARPA programs, including high productivity computing systems with IBM, ubiquitous high performance computing with NVIDIA, anomaly detection at multiple scales, power efficiency revolution for embedded computing technologies, hierarchical identify, verify, exploit, and software designed hardware. Recently, Bader received an NVIDIA AI Lab Award and a Facebook Research AI Hardware Software Co-Design Award. Dr. Bader is editor-in-chief of the ACM Transactions on Parallel Computing and general co-chair of IPDPS 2021, and previously served as editor-in-chief of the IEEE Transactions on Parallel and Distributed Systems. He serves on the leadership learn of Northeast Big Data Innovation Hub as the inaugural chair of the Seed Fund Steering Committee in 2021. ROI-NJ recognized Bader on its inaugural list of technology influences, and in 2012, Bader was the inaugural recipient of University of Maryland's Electrical and Computer Engineering Distinguished Alumni Award. In 2014, Bader received the Outstanding Senior Faculty Research Award from Georgia Tech. Bader has also served as director of the Sony Toshiba IBM Center of Competence for the Cell Broadband Engine Processor and director of an NVIDIA GPU Center of Excellence. In 1998, Bader built the first Linux supercomputer that led to a high performance computing revolution. He is a co-founder of the Graph 500 list of benchmarking big data computing platforms. He is recognized as a rock star of high performance computing by Inside HPC and as HPC Wire's People to Watch in 2012 and 2014. It's an honor to have you with us, sir. I request all the participants to their queries in chat will be answered at the end of the session. Now I request David sir to take over session.
You, Sri Haritha, for that very kind introduction. And I'm really pleased to be here and share this information with you.
John, yeah, some disturbance is there, no? Please. Yes. Oh, yes, Professor. Yeah.
Thank
Okay,
you.
Professor.
And my only disappointment today is that I couldn't be there in person with you in Mysore or Bangalore, where I visited many times and am really missing India with the pandemic and not being back to visit. So I hope on a future travel that I can meet with many of you. And also, if you come to the United States, I would glad to make you welcome. My research can be found on my website, so if you just Google my name, David Bader, you'll be able to find much more about the work that I'm going to tell you about. But I'm really excited to talk to you about solving some of the most challenging problems facing the world and using high-performance data analytics to do so. Also, I'm always looking for students, both master's and PhD students, as well as postdocs. So if you have an interest in these areas, please send me a note and I'd love to talk with you about some of those opportunities. And I'll tell you a little bit more about my research group today and the many students who have contributed to the work that I'm describing here. So as was mentioned in the introduction, a few months ago, I received the IEEE Sydney Fernback Award, and this was quite an honor and recognized me for the development of the first Linux-based supercomputer that was also on the national technology grid back about in the year 1998. And this has really led to a revolution in computing and really democratizing the use of supercomputing. And I'll tell you more about that during my talk. This has been an incredible journey, and I'm really pleased to receive this recognition. Actually, here's a photograph of the machine, and Larry Smarr, who is the founding director of the National Center for Supercomputing Applications, mentioned that this is of enormous historic resonance, being able to use commodity technologies to power the science and engineering that we're doing today. And also, this revolution has really impacted supercomputing. Now we see that all of the top 500 supercomputers in the world have switched over to doing Linux-based systems rather than the commercial monolithic systems and operating systems of the past. So this is now ubiquitous and has even led to the cloud providers and the ability to really serve compute cycles across many different applications and domains. So to tell you a little bit about New Jersey Institute of Technology, we're climbing the ranks as a top 50 public university. We're what's considered an R1 or a research-intensive university at the heart of Newark, New Jersey, and we're located just minutes from New York City, Manhattan. In fact, I'm in Manhattan at home right now, and it's just about 20 minutes on the PATH train to get to our campus in Newark, New Jersey. The institute that I run, I launched in July 2019 as I joined NJIT, and it's really focused in solving real-world grand challenges, everything ranging from urban sustainability to healthcare analytics, providing trustworthy, free, and fair elections, fighting insider threats within large organizations, protecting our utilities against attack, and also giving attribution to cyber attacks, and also looking at disease outbreak and epidemic monitoring, similar to what we've seen during this COVID-19 outbreak. I have about 35, at this point, about 35 to 40 faculty who sit in multiple centers working on these problems. There's a center for big data that focuses on big data analytics systems and tools, really the data engineering needed for big data and the cyber infrastructure development necessary to enable these high performance data analytics. We have a cybersecurity research center that's focused on practical encryption technologies, for instance, privacy technologies, information assurance, homomorphic encryption, and so on. There's a medical informatics center. We also have a fintech group. We're at the heart of the financial services and insurance industry in the Newark metropolitan region. And this is a very active group working with management and business, looking at data science opportunities within fintech. And finally, we have a new center in machine learning and AI that has many of our real world technologies and industrial partnerships. As was mentioned, I've collaborated and received awards from NVIDIA, for instance, running an NVIDIA AI lab. And if you use the open source Rapids toolkit, that includes our graph analytics inside that I'll talk to you more about today. And we've also worked with Facebook AI systems on scalable graph representation learning and looking at moving methods from toy exercises on laptops to being able to work in the enterprise, for instance, doing scalable graph learning. Now, I want to talk to you today about the bigger problem in data science, and I'd like to describe it along these two axes, where on the x-axis, going from left to right, I have objects, and I place known objects on the left and unknown objects on the right. On the y-axis, I have patterns with known patterns at the bottom to unknown patterns at top. Now, this divides the space of data science into 4 quadrants. And if I look at the lower left-hand quadrant, where I have known objects and known patterns, this is where relational databases have been doing a great job since the 1980s, where maybe I run a store where I have objects that I'm selling, items, I have customers, and they come in and they fill up their shopping cart and check out. So I know everything about the objects that I'm selling. I know everything about the customer interactions, and I can ask queries about what items are the most popular, what types of customers tend to purchase them, and so on. Now, in the off diagonals, I have areas, for instance, here in the upper left, I have known objects and unknown patterns. So to give you an example of this type of problem, maybe I'm the chief information security officer of a large firm, and I have my employees and I'm looking for insider threats. And here I may have an employee who's tripped up a number of tripwires, and I want to look around and see what is that person up to. And vertical databases have been very good at letting us explore around these types of problem spaces. Or in the lower right, where I have a known pattern, but an unknown object, is the case where I may have a template that I'm looking for in some larger observed activity. And I want to do a problem called subgraph isomorphism or motif finding within this larger data set. So these three quadrants we know how to handle quite well in data science. But where the challenges exist is in this fourth quadrant of unknown unknowns. And here, this is what I find very exciting. I'm passionate about trying to do data discovery where you're handed large data sets and you're trying to figure out what's there. Maybe you're trying to mitigate risk or reduce surprises or find new patterns. And it becomes a very exciting area to work in. But it's very unstructured. We need to figure out tools and questions to ask and algorithms to work in this space. For instance, machine learning works quite well when you have a known pattern that you can learn and you see many, many instances of it, and then you can recognize it in raw data. But here in this space, we don't have anything to learn. We don't know what we're even looking for. So we need ways to explore this fourth quadrant of unknown unknowns. So this is what I'm very passionate about. And when I see problems like this, what I tend to see in these data sets are relationships between objects. So whether I'm collecting system logs or I'm looking at sensor information, I often have these objects connected by these relationships. And I tend to turn those relationships into graphs. And I call it graph data science, where the vertices are the objects and those relationships turn into edges in those graphs. And this lets me work on many real world challenges by using this graph abstraction. And I argue that many problems today can be viewed as very large, or what I say as exascale streaming graphs. And by streaming, what I mean is that I don't have just one static data set. I have massive amounts of information coming to me all of the time. And I want to use that information to make better decisions and to analyze the data sets on hand. So whether that's from healthcare, for instance, detecting and preventing the next pandemic, or understanding massive social networks so that we can understand, for instance, how do communities' transportation systems work, how do you evacuate during an extreme weather event, and so on. Or business intelligence, trying to understand anomalies, or discover knowledge from massive data sets within your companies and monetize that knowledge. In systems biology, we may be trying to do personalized medicine or drug design. For our electric power grids that are important for our communication networks, transportation, energy, even our water and food supply, we want to make sure that we have a resilient power grid that is not going to be able to be attacked by adversaries or go down if an element on the grid fails. All the way up to performing full socio-economic political simulations of entire nations. All of these require predicting and influencing change in real time and at scale. So we have two challenges here. One is the size of these data sets is typically, it's just enormous. It will overwhelm a laptop. And also we want to be able to work on these data sets in near real time. We don't have hours or days to crunch the data. We want to be able to do it and ask our questions and get answers in real time. Now, when I talk about graphs, there's many, many, many types of graphs. These sources of data that we typically see are coming from, for instance, computer simulations, experimental devices, off the internet, from scientific applications. We can get data from all sorts of sources. And this raises new challenges, for instance, in the data sizes, also the heterogeneity of the data sets that we want to bring together, the uncertainty and, for instance, the noise and bias within the data, and even the data quality that we have. So we're faced with many challenges, and what we want to do is design algorithms that will solve the real world problems that we're interested in. So let me give you 3 examples here. On the left, I have an example from astrophysics where maybe we're looking at the sky and there's digital sky surveys. These are some of the largest data sets in existence today. And maybe we're looking for pulsars, which are a celestial event where there is a pulse of light. And we only have minutes to turn a big radio telescope to look at that event. So what we do is we look at these digital sky surveys and look at two overlapping images and look for changes between the two, for instance, outliers. And then we're going to be challenged because these are some of the largest data sets that I mentioned, and there's temporal variations as we look up at the sky that we're going to have to account for. And the graph problem then that we may be trying to solve is something like clustering or matching between these objects. In the middle, I have an example from bioinformatics where maybe we're trying to identify new drug target proteins, but we're challenged by the heterogeneity in these data sets and also the quality as these come from clinical labs. And the graph problems we may be trying to solve are ones such as centrality or clustering. And on the right, we have a social informatics problem, a social network, where maybe we're trying to discover emergent communities within the networks, or maybe we want to model how information spreads around the network. And we're challenged with trying to design new analytic routines and also all of this uncertainty that we have with social data. And the graph problems we may be trying to implement are ones related to clustering. Maybe we're looking for shortest paths. Maybe we're looking for flows. And so when we talk about graphs, there's really many types of graphs and different properties of the vertices, of the edges, and even the different types of algorithms that we'll want to run. Here's an example from looking at the United States electric power grid, and this turns out to be a large graph problem to try to protect it from failures and anomalies within the grid. And we know that a small outage can cause a major blackout across this electric power grid. Or maybe for intelligence and surveillance, we need algorithms. For instance, at the top is the US 9/11 terrorist network. And it was argued that if we could run an algorithm like betweenist centrality based on shortest paths within the graph, we would have been able to identify the hijackers on these flights. Or on the bottom, this is an example from communications of the ACM, where we have a pattern that we're looking for, and with graph matching or subgraph isomorphism, we'd be able to find that pattern in larger observed activity. For instance, in this pattern, we have two people that live together. One is renting a truck, one is buying fertilizer, and they're observing a factory. And it's argued that this is a potential pattern for constructing a bomb we may want to see, and is there any instances that look close to this pattern within the observed data? So this is how graphs have gained some importance in the last decade for solving some of these very critical problems. And even in public health, this is a snapshot of a problem that I worked on with my PhD student, now a professor at Penn State, Kamesh Maduri, where we looked at the human proteome. And at the time, there were about 44,000 human proteins that have been observed. And we want to understand the importance between these proteins. So we mapped them onto a social network based on the protein-protein interactions in the human proteome and ran an analytic called betweenist centrality. And what I pictured here is a normalized plot of each one of these proteins is a dot on the graph. And this is a log-log plot. So the X and Y axis are both on logarithmic scales. And on the X-axis, I plotted the degree of each protein. And the degree means how many other proteins does this one bump into. And on the Y-axis, I have the betweenist centrality score. So highest means that it's more critical in the network. Low betweenist centrality means it's not as important. So what you observe, first of all, is that the highest betweenist centrality protein that I've highlighted here and circled isn't the one that has the most friends in the social network. It's not the most interactive protein, but it turns out to be very critical and has been implicated in breast cancer. So we see more and more, this is like trying to find a needle in a haystack, that running graph analytics like centrality is able to find hidden objects that aren't necessarily the ones that are the largest degree or the ones that we see most often, but are somewhat hidden within these networks. So all of these graph problems require us to go through a thought process of what are we trying to solve and how do we do it. So I'll go through this very briefly, that our input is typically a graph abstraction from our real world problem. We'll map it into the language of graphs and then decide what are we trying to find. Is the problem to find a path, clusters, partitioning of the data sets, matchings, patterns, ordering? What is it that we're trying to find in the graph space? And then based on the different attributes of the graph, we can decide what algorithm to use. So for instance, is it a sparse graph, meaning that the ratio of edges to vertices is low, or is it a much denser graph? Is the graph static or fixed, or does it change over time? Are there weights on the vertices or weights on the edges? And if we do have weights, what is the distribution of the weights? Are they all integers? Are they coming from some range? What type of distribution do they come from? Also, the vertices, do vertices have a fixed number of neighbors, or is there some degree distribution where we have both high degree vertices and low degree vertices? Are edges directed from one vertex to another or undirected? What's the size of the problem? And so on. So all of these factors we use to influence what graph algorithm we're going to implement. So the algorithms that we have may be traversals, we may be looking for shortest paths, flows, spanning trees, topological sort, and so on. But the choice of that algorithm is influenced by all of these factors within the algorithm. So to be a smart graph analyst, we're going to have to understand the types of data sets that we have and these factors within the graph, and then make the right choices for the algorithm to employ. And sometimes we'll implement this directly as an ad hoc graph algorithm. Other times, some graph problems are often recast in different languages. For instance, in sparse linear algebra that we see a lot with partitioning problems, or maybe we'll use linear programming, for instance, for matching computations. And so we may often view the graph in different ways to solve the problem. Now, supercomputers have been great for some large-scale graph problems, but typically only when the graphs are static and we can load that data set into a big supercomputer, and also when the graph is fairly dense. I like to think of this as reporting the news. So imagine there's some egregious event. You're in a company and there's a data exfiltration, and you say, oh my gosh, let me collect up all the system logs and analyze them to see how did that intruder access our internal systems, how did they get in, what did they touch, what did they take, and how do I protect against this in the future? But you're doing that after something egregious has happened. Where I'd like to get to is what I have on the right side, which is predictive analytics, trying to use streaming analytics to be able to understand the situation and stop bad events before they ever happen. So this is something that I'm very passionate about, and a place where I think we're on the path to be able to solve, but it's going to require a lot of hard work. We're going to need specialized analytics and data structures, and also know that our data structures aren't fixed, but we're going to need rapidly changing data structures for these irregular and combinatoric problems like graphs. And there's also very low data reusage. So caches may not be as helpful to us. We want to focus more on the memory subsystem and memory operations and our data placement rather than floating point operations per second. And I think we see a shift in computer architecture to be able to try to address more of these memory-centric types of computation. So in graph data science, we're going to be looking for new types of graph techniques, and do they scale? And for instance, there are a couple types of analytics that we're going to want if we're looking at, for instance, communities within these graphs. We may want to detect both static and emerging communities. Maybe we're trying to find important individuals or vertices, detect anomalies, and so on. We're going to want to do this at scale. So the way I'd like to define the framework that we need to set up is with this, this example. And while I'm talking about social networks here, just know that this abstraction of a social network applies across all of the domains that I've mentioned. Wherever I have vertices, you consider them as people, and relationships between those objects, consider those as actions that occur across the network. So for instance, here I have a person, and this is person A, and at time 1, she has an action like poking person B. So we can take every action in the real world and replace it by a tuple, where here it's a 4 tuple. We have 2 objects A and B, a timestamp T1, and an action like poke. So here's person B. And maybe at the second time T2, person A now sends a message to person C. But also at time 2, person B receives the poke that person A sent at the last time period. And maybe at the third time step and fourth time step, we have all of these individuals taking actions, and they'll induce all of these tuples. And you could consider every one of these tuples as an edge, where the 2 objects, for instance, A and B, are vertices, and then there are attributes on that edge, like a timestamp, and then the attributes of the type of action that took place. So we could funnel all of these into a stream, just a massive stream of edges, edge 1, edge 2, edge 3. And this is a continuous stream, and we're going to want to put that into the memory of a supercomputer and have that computer think about the state in terms of a graph that's rapidly changing over time. So it's a dynamic graph, and here I've represented it as a cartoon where I have different types of vertices given by colors, but I could have different types of vertices, different types of edges, directed edges, undirected edges, and so on. And then my analysts who are on the side here want to ask questions, and what they're going to do is pose their question to that computer and ask that graph a question. And potentially they'll be asking multiple questions all concurrently on that graph. So this is what we're trying to create a system that will do this, and to be able to ask all of these questions concurrently. Now, once we start including time into our graph, we have to think more about graph algorithms and how to incorporate that temporal component or time. And I like to categorize it into 3 types of queries with time. In the first category, we're really taking our sequential graph algorithms and simply using time as a window or as a snapshot. So for instance, you may want to ask a question, is there a path between 2 vertices S and T? And with time, now you may want to find a window and ask, did that path exist between time T1 and T2? Or for instance, you may be trying to look at all the important vertices at a particular snapshot of time T. And so this is very straightforward. It's very natural to think about all of our static graph algorithms in terms of windowing or snapshots. But where I think this is really interesting and where we don't have a lot of research yet is to look at the next 2 categories. In the second category, we're essentially monitoring properties or doing change detection. For instance, does the path between 2 vertices drastically shorten, and can I alert someone whenever that happens? Or is there some vertex that was hidden before that suddenly became very central? I may want to let someone know about that. And so this is really persistent change detection within the graph. And I think this is a very interesting area for streaming analytics. And finally, the last property are asking graph algorithms that are truly dynamic, fully dynamic in nature, where there is no static analog. For instance, is there a small community in the graph that stays independent, meaning no edges occur between that small community and the rest of the graph through long periods of time? Does it remain active and separated? And what exactly is it? Or is there a vertex that was core in one community, but over time became core in a different community? And why did that happen? So these are what I think of as fully dynamic inquiries to that graph. So this raises new types of queries, new types of challenges to be able to deal with these types of questions. Now, to tell you a story, just over 10 years ago, we were the very first research group to take all public tweets and to do graph analytics on the entire set of public tweets. We looked in September and October 2009 and took all of these tweets and rooted it into a supercomputer and built a graph out of the follower and followee network as it changed over time. And at the time, there was another pandemic called H1N1, an influenza virus that was being considered to maybe have double-digit mortality rates around the world. And we wanted to see, how do people get the best information during a breaking event? Was there any value to Twitter to be able to figure out what is the most newsworthy source out there? And so on this list, we're able to run an analytic called betweenness centrality. And on the left-hand side, we have some ad hoc results where we were able to pick out some of the important news sources. For instance, the US Centers for Disease Control and Prevention, and that's at number 1, CDC Flu, number 4, flu.gov, number 11 and 12, CDC Emergency and CDC eHealth. So that's great that we were able to find that. But we also found commercial media sources like number 5, the New York Times, number 8, CNN, number 11, Time Magazine. And so this has been, some obvious things that we're looking for. But then we had some surprises, and this was where the value of this massive scale graph analytics came from. For instance, number 3, official PACS, was highly influential for people to get information about H1N1, but it was not the place where you tune your dial to try to understand what was happening in this breaking event. It turned out that official PACS is the Twitter handle for a mostly adolescent male gamers convention called Penny Arcade, and it was a set of individuals gathering in Seattle in the United States, and they're the first group to get H1N1 and publicly start tweeting about the symptoms and their positive diagnoses and what the repercussions were. And it turned out to be not as deadly a pandemic as was expected, but we were able to discover this very influential handle that was quite a surprise. So this is the power of streaming graph analytics, to be able to take a lot of information and get to the source of these really influential handles. We call this work now STINGER, standing for Spatio-Temporal Interaction Networks and Graphs. And we use these streaming graphs in this framework to try to solve these real-world graph problems that I've mentioned before. But unlike traditional high-performance computing applications, solving these problems at scale really raises a lot of new research challenges. For instance, we have these sparse data structures with not a lot of locality for the graph algorithms. We have to design new parallel algorithms that are really having high fidelity to noisy data and these large problems. And also, we need to design more computers that are energy efficient, resilient, and easy to program, which is an ongoing challenge. So our framework, Stinger, has been in development for many years, going back 10, 15 years or more. And over time, we've had many firsts for streaming algorithms. For instance, we won the Best Paper Award at IEEE HPAC in 2010 for this work. We had the first dynamic betweenness centrality algorithm about the same time, streaming connected components, streaming community detections, and even the first incremental PageRank algorithm that is very fast to update PageRank rather than having to recompute PageRank across an entire data set. And then about 5 years ago, we started specializing for GPU acceleration in a package we called Stinger, and then later Hornet, that was specialized for the GPU. And this is the package that now sits within the Rapids AI framework from NVIDIA, the open source data science toolkit, where Hornet has become integrated with cuGraph within the NVIDIA Rapids AI package. And for GPUs, we've had many algorithms now that accelerate both on single GPUs, but also multiple GPUs for doing these streaming graph algorithms. So I encourage you to pick up this software and to try it for yourself. I won't go through all of the details of Stinger. It's a dynamic graph data structure that allows for parallelism across vertices and edges, and also allows the graph to change underneath as you're asking queries of that graph. And we've used Stinger in many real-world applications where it can ingest different types of data sources, for instance, JSON, CSV files, text, even random edge generators for testing. And then these analytics can run off of the Stinger server that holds the graph. And some of these analytics may even be able to call other analytics to produce the analytics across all of these algorithms that we've encoded and produce results for an analyst. So this is available from stingergraph.com. It's got many of the streaming versions of graph algorithms, for instance, clustering coefficients, connected components between a centrality and community detection, and quite a lot more within this package. It's been quite a workhorse, and it's all open source, so you can take a look at the algorithms. But we needed to do this because traditional technologies were not able to solve these massive graph problems. For instance, traditional SQL databases don't have the structure to do meaningful graph queries. There are graph databases, but typically they keep the data on distributed disks, and they're very slow to operate when you're operating at disk speed versus in memory. Hadoop and HDFS-based projects also have graph solutions, but they're really not the right programming model for many of these structural queries over the entire graph, and random access to Hadoop-based systems often leads to poor performance. There are some graph libraries that are quite popular, but often they just run in a single socket, for instance, on a single CPU, and they can't scale to these very large graphs. So we purposely had to build this new technology. I'm also excited by a project that we've recently undertaken. I'll just tell you a little bit about it today. And I'm excited because it really democratizes supercomputing for data science. And it's a project called High Performance Algorithms for Interactive Data Science at Scale. We're taking an open source data science toolkit that was recently started in 2019 called Arcuda. And Arcuda is the Greek word for bear. And it lets us take massive data sets, but be able to ask data science questions in the lingua franca of data scientists, which is running Python queries within our Jupyter notebooks. So we get the productivity of Jupyter and Python, but the performance of a supercomputer. And we let everyone who wants to be able to solve these problems run with a supercomputer in the back end. So it removes the interface barrier to complicated and low-level parallel programming, and the resource barrier, being able to directly utilize supercomputers seamlessly rather than having to construct your own machines and connect to them from your PCs. So this provides a tension, though, between that productivity and that performance. And what we're doing is we're building out graph algorithms within this large data science framework. And you can think of Arcuda as a replacement for your NumPy and Pandas that you typically use within Python. And we replaced the functionality with Arcuda, and it's just as easy to use. But what we have is the use of Python for productivity that the user programs in. And then what we're doing as developers is implementing supercomputing data science and graph algorithms using the HPE Cray Chapel compiler, which is also open source. So everything that we're doing here is open source, both Arcuda and the Cray Chapel compiler. And what happens is the user just interacts with their Jupyter notebook as they did before writing Python with Arcuda. And what we're doing, all of the hard work, is to make this transparent that there's actually a message queue to a Chapel server that holds the graph in distributed memory or in a cluster or laptop, wherever it happens to be running. And all of the hard work on massive data sets is happening on that back end, but the results are then being reported back to the user seamlessly so that the user doesn't see any of this complexity to the problem. And this allows the analysts to scale beyond megabytes data sets. We're targeting tens of terabytes and allow Chapel to manage these multi-tens, dozens of terabytes on the back end and have queries that happen in near real time, but have the supercomputer in the back end doing these types of computation. So at the bottom, I have a couple links, and I encourage you to go to our GitHub and to look at this code, take a copy of it, and see what you can do with it. It's quite exciting to be able to work on these massive graph problems and do it with our CUDA. Again, it's early in development, so it's only a couple years old, but I'm really optimistic that doing data science and large-scale graph analytics in our CUDA will be a great capability to many organizations. Now, I don't have time to go through all of the innovations that we've had with implementing within our CUDA. So I'll just give you a couple highlights that we've created new graph data structures that are very efficient for both undirected and directed graph. That is the storage within the Chapel backend rather than the Python front end. And also we can load balance the graph partition by balancing the edges across the compute resources rather than just the vertices. And so this also lets us balance our operations across our system. And we've been able to implement graph algorithms at a massive scale like breadth first search. And here's just an example graph with the source vertex 0, and breadth first search is trying to find the distance from that source to all the other vertices in the graph. And the output would be a vector of those distances for each one of the vertices in the graph. And that would basically induce a partition of the levels of the graph. Each level has vertices all a fixed distance from that source vertex. So we can do this in our CUDA. This is the code. I won't go through all the details for both the high level and multi-level, multi-locale breadth first search algorithm. So it's pretty easy to implement, and we've been able to run it quite well on a variety of different types of graphs. So I won't go through all of the performance numbers here, but needless to say, we've been experimenting with different ways to parallelize the results, and we take all of what we've learned through this experimental algorithmics, and we've incorporated it into the CUDA package so that you, when you run CUDA, get the fastest results possible across many different types of graphs. So to conclude, really, CUDA and Chapel can be used to handle much larger graph analytics, and it gives you both the high productivity to make this seamless for the data scientist and easy to use, but also very high performance for some of the most challenging graph analytic problems. So to conclude the whole talk, massive scale analytics really requires new high performance computing platforms, streaming algorithms, especially graph analytics, and something that I didn't talk about as much today, but energy efficient implementations, whether we're using our smartphones all the way up to supercomputers. But if we can map our applications to the right high performance architectures, we may get improvements that are 6 or more orders of magnitude faster. And this enables us to do what we really started to do, which is to make the world a better, safer place, more enjoyable, by solving some of these real world challenges that I mentioned a few times during this talk. For instance, in urban sustainability and reducing congestion in our road networks, finding personalized medicine and personalized healthcare, making sure that we have fair and free elections, fighting insider threats and lone wolf actors, also protecting our utilities against attack, and giving cyber attack both defense but also attribution to where those attacks came from. And finally, monitoring disease outbreak and epidemic monitoring. These are really the types of problems that we want to solve, and we're really focused on these types of problems. I want to acknowledge my research scientist, Dr. Zihui Du, some of my current PhD students, Oliver Alvarado Rodriguez and Fuhan Lee, and a former PhD student, Oded Green, who's now at NVIDIA, for many of the contributions here. And some of my recent alumni, Dr. Isha Nathan, she's at Lawrence Livermore National Lab, Dr. Vipin Sachdeva, Dr. Anita Zashkrushka, who's at Trovaris, another big data company, Dr. Luis Miguel Mungia, who's at Google, Professor Kamesh Maduri at Penn State, Dr. David Ediger at GTRI, the Georgia Tech Research Institute, Professor James Fairbanks, he's now a professor at University of Florida, and finally Dr. Sunghwa Kang at NVIDIA, were most of the contributors to the work that I presented here. So thank you again. I'm very glad to be able to have spoken with you. I encourage you to reach out to me. You can Google my name and find my contact information and send me a note if you're interested in talking further or working with me. So I'd like to stop the slides at this point and see if there's any questions that you have for me. And I do see that there are some in the chat that I'll try to get to. So let me just pull up the chat. And there's a question that says, very interesting work. Firstly, you have one slide where you mentioned 3 types of different dynamic graphs that require further research. Do you think GNN, GCNN can help? Secondly, how much does the memory of the processor architecture play a role in the streaming graph? Those are 2 great questions. I do think that there's a lot of excitement now about graph neural nets and graph convolution neural nets. And there is a relationship. When I think of data science, I think of the combination, the power of using both machine learning like GNNs and the graph analytics and ad hoc analytics together for more functionality. In fact, we're starting to work with a company called GraphCore that makes a specialized graph neural net architecture and use that for doing both graph algorithms and graph neural nets combined together. So I think that there is further research needed as these techniques really combine powers together. And in terms of memory, memory is very critical for what size of state we can hold for that streaming graph. When our memory is very small, for instance, we've used Raspberry Pi with just tens of kilobytes, we can have a very small graph that represents maybe a few seconds of graph history. But when the graph memory is, when the machine is very large and we have terabytes of memory, maybe we have a 10 terabyte machine of RAM, then we can store maybe a year to 10 years of our graph in that memory. And so it depends on the type of application we have. If it's a cybersecurity application where we're looking at a very long-term advanced persistent threat over years, we may want to load our cybersecurity and network logs into a very large memory system to be able to look over multiple years to understand patterns and attacks. So it really is, our problems are going to be very dependent on how much memory we have available. So I don't see other questions yet in the chat. Thank you for all of your comments. But if you'd like to unmute and ask a question, I'd be glad to answer any other questions.
Yeah, Professor, thank you. It was very nice session. Actually, it is very interesting. And actually, we believe that this, whatever the topic you shared, it helps the participants and create interest in them to develop the deep into these subjects. Actually, we are very grateful that you spent the you spared your precious time with us. Actually, thank you. If anybody is having any authors, participants is having any questions, so please unmute yourself and you can ask. So one more questions in the chat window, Professor. Actually,
I see a question asking about hardware acceleration, and that's a great question. Okay. In fact, much of my prior work has pioneered the use of GPUs for acceleration. I think GPUs are fantastic for being able to being able to accelerate these types of data science applications. And also we see specialized architectures. I mentioned GraphCore, but there's many architectures emerging to look at accelerating these types of data science problems. So more and more, we're going to see acceleration, especially as we start to nail down what are the algorithms that are needed and the data structures that are needed as well. So these architectures, I really encourage you to take a look. It's an interesting area right now. We're working on some problems in that space. And again, I mentioned before, if you're interested in both hardware, software, co-design for graphs and data science or any of these graph analytics, I am looking for master's and PhD students and postdocs as well to work in these areas. We have some partnerships emerging with NVIDIA and ARM and other companies like GraphCore and IBM and Intel, etc. So please reach out to me if you're interested. I'd love to work with you. Or, these are very interesting areas for you to hopefully pursue as well in your research at universities or at companies.
Yeah, thank you, Professor.
Thank you so much.
Yeah, I request the participants to please switch on the camera. We can have one group photo. So before proceeding further. Yeah, thank you. Yes, Spurti, please go ahead.
So, it was such a thoughtful webinar. I hope the knowledge gained from this webinar would be thoughtful to the young minds present here. As we have come to the end of the webinar, I request Sri Harshita P. to render the vote of thanks.
It was a great webinar, sir. As we have come to the end of the webinar, I'd like to extend my heartfelt thanks to Dr. David A. Bader, sir, for the great information. Thank you, sir. I'd like to thank Dr. Deepa Shanoy, Chair, IEEE Bangalore Section, and Professor UVCE Bangalore. Thank you, ma'am. I'd like to thank Dr. Parmeshachari BD, Professor and Head of the Department of Telecommunication Engineering, Chair, IEEE Mysore Subsection and IEEE Student Branch Counselor, GSSS IETW, Mysore, for constant support. Thank you, sir. I'd like to thank Dr. Jalaja S., Chair, IEEE CAS Bangalore Chapter, Associate Dean, BIT Bangalore. Thank you, ma'am. I thank all office bearers and EXCOM members of IEEE Mysore Subsection, IEEE Bangalore Section, IEEE Information Theory Society Bangalore Chapter, IEEE Circuits and Systems Society Bangalore Chapter for conducting this webinar and support. And I once again thank all those who are present and making the webinar successful. Thank you.
Yeah,
Thank you
thank
all
you.
and have a great evening.
So much.
Professor, thank you. Once again, thanks a lot for giving wonderful talk for all the participants. The participants were appreciated the talk actually. It is an excellent talk by you, Professor. Thank you.
Thank you. And I hope to visit you in India in the coming months. Best regards.
Yeah, sure, sir. Yeah, sure. Thank you. I request the participants to please download the certificate from the link shared in the chat window.